Let's continue with what we had last time. This is what we had last time. We started with the state of stress, and I'm going to put that state of stress here, which looks something like this. So I'm sorry, I forgot to put that, which was, here was 12.3 KSI. Is that correct or not? Yes? Which was x, sigma x. And then we had a sigma y of 4.2. Is that correct or negative? Because that was the compression stress. You are designing something like a plate. This is what you see. And then we had a shear stress of 4.7 KSI. This was our state of stress. This was our Borserker, yes or no? And then we decided, okay, this is principal stresses, A and B, one principal, two, they have no shear. What is important here for you from now on is to recognize three things. One, when you started this plane, this could be in XY plane or YZ plane or XZ plane. Everybody understands it doesn't have to be exactly X and Y. We usually use X and Y because even if it was in that plane, I can change it to X and Y. Everybody understands it because that's typical of math problem there. And then you have to recognize something else for today's lecture, and that is this is not a square. This is a cubic. Everybody understand that what I'm talking about. Objects are 3D. Is that correct? You are designing a shaft, a building, an airplane, part of a landing gear of an airplane. That's a 3D body. Is that correct? But when you look at the surface of that, it looks flat. Is that correct or not? That's why we call it 2D. And that's very important to recognize that. So in reality, this was like this. Is that correct or not? Yes, with the X and Y and Z axis like that. Then there is a discussion here, which I'm going to do after we finish discussing. I'm a little bit behind there. So what we did, that is what? The first problem that you were facing in ME 218 was, okay, numerically, you can find all of it. Maximum shear, let me put that one down. The maximum shear is also equal to R for this problem. Is that correct or not? And R was 90, how much was it? 9.49 KSI. Now, the only thing that I went quickly, I show you the picture, but I didn't show it to you. I'm afraid that you may not be able to do it, but I'm sure that you understood it, is how to plot the principal stresses in the direction you want to. Is that correct or not? It is easy, or we already know that. You have to understand that. This is X and Y. This is either going to rotate clockwise or it's going to rotate clockwise to get to the principal stresses. But that shows you everything. Everybody understand that. So if this is X, which is this actually is not a point. This is the direction. Everybody says, oh, we call it an axis. Is that correct? That represents this surface perpendicular to the x-axis, which has one sigma and one tau. No matter what you are designing, there is always two types of stress, sigma and tau. That's it. There is no other stresses. Is that correct? Or even it's a temperature or etc., it turns out into this. Torsion turns into this. Transfer shear turns into this. Tension, compression due to the P, due to the M. Is that correct or not? This is it. One sigma, one tau. Is that correct or not? So when you look at it, this stress 12.34 actually represent the x-axis. Yes or no? This one represents the y-axis. There is a z-axis. Can you show me where is the z-axis there? This is something for today's lecture. Actually, we haven't talked about it before. But since I'm doing this problem, at the same time, I'm giving you new information. Where is the z-axis? What kind of a stress do we have in the z direction? Do we have any? No, no. No, in all the problem we had, there were no stresses in the z direction. So stress in the z direction is 0. I'm going to mention that again. I talk about it in ME 218 about the plane stress. And everybody, now there, we just let it go. Here, half of the class is about plane stress or not plane stress. We'll talk about that. The whole chapter 11 or 10, I don't remember which one, or 9, whatever, it's all about plane stress or not being plane stress. But however, let's leave it at that. But remember this. This was because I see sigma x. You see, this is what we see. This one, and that one, and that one, and that one, and that one in general. I put it all positive. Everybody see that? It turns into that. Is that correct or not? Yes? Ignoring the, in a way, z-axis. Is that correct or not? Yeah. OK. Now the point is, how do we get from xy axis, which is this one, to the principal axis? Obviously, we did that this last time. We have to go clockwise. Yes or no? But look at this. This is what I'm going to say. If you look at the picture in your handout, which I show it to you, when you go in this transformation, that tells you exactly what happened. X become A, Y become B. Everybody does. That's not always true. Sometimes X is here. So if X goes there, you have to go this way. Everybody understand that? X become B, Y become A. Somebody asked me, how do we decide which side to put X, but that's about the rotation that you are having there. Is that correct or not? Now, notice I went this way. If you look at the picture is that way. Is that correct? Yes. If I rotate clockwise, I get to A. Everybody understand that? If I rotate counterclockwise, X become what? X become B. Actually, when you calculate this angle, there are always, everybody knows that from trigonometry, there are two answers for each tangent or sine or cosine. Yes or no? 1 plus 1 minus. So look at the picture now one more time. This is what will happen. So in other words, you get now X and Y, and then you rotate that. I put it here for the benefit of camera. So as you see here, I put here X, and I put here Y very lightly. Then I rotate that how many degrees? Not 29, half of that, which is 14.8. So I rotate that 40.8 degree and like this. And then I put my side like that. Now, this side is perpendicular to this direction. Let's call it X prime. And this direction will be Y prime. But this time it's not X prime, Y prime. In that operation, X become what? X become A, Y become. So this is the direction of principal stresses. Let's call this one principal 1 and principal 2, because one is A, the other one is B. What do I put at A? At A, I put this and 0. It's very important. Everybody, and there is no shear stress. So therefore, I put here 13. It's in tension. So I put here 13 point, whatever it was, 34 or 54? 13.54. So 54 KSI. And on the other side, because Y become P2 or B, X become P1 or A, this become P2 or B. Either way, you can show it like that. And that one was, of course, a negative of 5.4. So this is it. Is that understood? Yes or no? Yeah. And there is no shear. Remember that. When there is no shear, it is all principal stress. Because on this circle, each point actually is an axis going in certain direction. Everybody understand? The whole circle represents all the stresses. You find the stresses at this point. Then all the stresses in every direction is represented on that circle. And then these are at the same point. You are not changing the point. However, one of them is the largest, so you design the object for this one. Is that correct or not? Now, what happened here now, I want to calculate the shear. This is the one I want a little bit interested. Everybody can do that. Now, this time, which way should I go? Now, I don't need this. OK? Now, look at the handout, guys. Look at the handout. Look at that picture one more time. Look at the handout at the bottom of page 18, I believe it is. But not the new handout, the old handout. The new handout, I have not started yet. These are still, we are on the old handout. Look at the bottom of the page, what is this, 18. Look at that. That's the state of stress. Look at the bottom of the page, yes or no? Correct? You see that picture given. But he didn't go that way. He does not showing that. He shows that one. What angle is that one? Look, I'm showing, I erased it already. That angle was 75.2 because they went this way. But X become what? X become B. Look at this one, guys. If I go that way, this is x and y. If I go that way, x become b. Is that? But I went the short way because it's easier to go to short way. Everybody understand it? Yes? All right, good. Now we can do the same thing for the maximum shear. But look at the coordinate here. What's the coordinate of D? How much do you have a sigma? Sigma is not equal to 0. Many people would do that, make mistake. At C, a center of coordinate, we have an average stress. Yes or no? The average stress of 4.05, but this is plus 9.4 plus R, and this is minus R. Is that correct or not? Yes? How do we put that on a element? The answer is that, but don't look at the answer. That's what I'm saying, that if you look at the answer, you get the wrong impression that whether you know it or not. Let's do it ourselves and match it with that. Is that correct or not? Yes? So which way should I go now this time? This way. This is your 2 theta s, which I don't have to calculate that because these two lines are perpendicular to each other. So if I have one, I calculate the other one. These two lines here are 90 degrees. On there will be at 45 degrees. Remember that. We need that information for today's discussion as well. So therefore, anyhow, I have to go how many degrees? I have to go, here become 60 something, here become 32, but it will be counterclockwise. Yes or no? Therefore, again, you get your x and y very lightly there. This time you go a little bit more, so you are going 30.2 degree or whatever that was. Yeah, 32 degree. You put your two line here, and you draw your element there. Is that correct or not? Yeah. Now, look what happened here. This is x. X become what? Look at here. This is it. So if I go color-wise, this is what I did in AME 218, so I might as well do it here. Yeah. This one is black. This one is green. Yes or no? Those green are here. Is that correct or not? Yes? The two axes are green. Now let's call the other one blue, or some other color, or purple, or whatever you like. Let's use it purple. We are now looking at this axis and this axis. Yes or no? And those are here. Correct? Right? Look. I went from x and y to this. Yes or no? Correct? X become what? X become D, because look at this. You are going like that. Is that x become D, y become E. So you look here, x become D. This is D axis. Is that correct or not? Y become E. Each problem has its own system. Here I have x and y here. One of your problem, x is here, y there. So you have to do something according to this rule. Is that correct or not? Yes? Mm-hmm. Yeah. Now what's the coordinate at point D? Read it as it is. 4.05, which is tension. Yes or no? So you have a tension of 4.05, which on the other side will be equal and opposite. All right, that's no problem. Then what is your shear value? Positive. But remember this arrow, guys? Is that the way we show that here? This was sigma versus tau, yes or no? If it is positive, I should go that direction, yes or no? If it is negative, I should reverse it, yes? This was negative, that was positive, yes or no? That's the way we draw the Mohr circle, according to Mr. Mohr. Is that correct or not? Therefore, if it is positive, I must be going that way, yes? Look, I'm coming here. Which is that way? Look, this way, correct? So, like that. Is that correct or not? Yes? Now we go to the other point. After this rotation or this transformation, y become E, yes or no? I already did that. X become D. Now I have to worry about the other side. Y become E. Is that correct? What do we have at E now? This is the E direction. What was that? We have also 4.05, which is that's average stress. Is that correct or not? Yeah. What shear do we have? Shear this time is negative. It's negative. It should be going that way. Yes or no? That way. Look, I'm handling that same thing. So it should be going. Oh, something is wrong. This was positive. The other one should be negative, so I'm sorry. It should be going that way, yes or no? It should be going that way, yes. All right, sorry. My hand was in the wrong direction. That is correct. Everybody see what I'm talking about? It should be going this way, yes or no? Counterclockwise. So therefore, it should be going that way. So if that is the case, you end up with exactly like before. Everybody understand what that? The head are together, the toes are together, and that's what you see on the bottom of the page as well. Is that correct or not? Yes? Correct?
Yes, sir.
Good. So this is what I left out last time, that I couldn't do that. So now let's continue with the discussion. A few very important points here, guys. One important point is this. There are 3 axes, I showed you already, yes or no? And there are also this rotation. When we do that, all the rotation is like that. I want you to consider this. This was our state of stress, yes or no? Look at this shear, yes? When I want to go to the principal stresses, actually I want to get rid of my shear, yes or no? Either I go counterclockwise or I go clockwise. For this problem, we went clockwise, yes or no? When we get to that scenario, then there is no shear here, yes or no? Correct? And then if I want to find the stresses at any other direction, I can do that too, yes? Let's do that part. I almost forgot about that. Let's find out the stresses now at the same problem. Please write it down. This is something I did for the other class, so before I go to the next discussion, let's do that. Now find the stresses. This is a new question. The same problem, find the stresses at theta equal to minus 40 degrees. Especially last time I asked you, one of you guys in this corner, you said you can do it. Is that correct or not? I think it was in this class, somebody asked me. There is 2 ways to do that. One way is using the equation, 7576 and 77, which was at the beginning of your handout, yes or no? Notice, I want to repeat this now for those of you who came late. In this problem, you can use all the equation. For this problem, you are not to use you have to use this technique. This is by graphical method. Everybody understand that. So by graphic, and everything is come from there, no equation. Problem number 1 and 2 from handout, homework number 2. This is the last page of, look at your handout there. Somebody made a mistake there. There are 2 homework assignments. Homework assignment 1. This is homework assignment 2. It's all about the Morse circle. Go to that, yeah, that one. So there is 3 problems there. Problem number 1 and 2 is your homework. Problem number 3, probably I'll do it in class. Everybody understand that. But this is something you already learned in the past. It's a little bit more maybe sophisticated than before, because now you are practicing more and more. But those are the combined stresses, which we are going to talk about it a little bit later as well too. So therefore, problem number 1 or 2. Now, the rest of it is new material, which I'm getting at it now in few minutes. Is that correct or not? Yes? Now, let's answer this question, which is the remaining question. As I said, one option 1, write it down. Option 1, which is obvious to use equations. If you are using equation, I don't know, it was 75, 76, and 77, which is in the handout, and it was in the book as well. Is that correct or not? But that is one method. The other method, using the Morse circle. That's something some of you already have done it or not. But to do that, you don't need all of this information. None of this is required. However, drawing the Morse circle is essential. Is that correct or not? At least to this point. You need to calculate, put the x and y there, which we did. Correct or not? Yes? You don't need to calculate A and B. That's not necessary. But you need this angle. That angle is 29.6 degrees. Now, what's the object of our exercise here? Is this, guy. We don't want to go to the principal stresses. We don't want to go to the maximum shear. We want to find the stresses at minus degrees. So in other words, I want to go like that. This is 40 degrees. Everybody understand that? Yes? So this become x prime, and that become y prime. Find the stresses along x prime. This could be a welding surface. It could be somewhere that you are interested to put something there. Everybody understand that, and you are interested to find the stresses on that, the body of some machine part. In that, sometimes you two plate together, and you want to find out the stresses in the direction there, which you can read it, go this way, that way. Is that correct or not? Yes? Mm-hmm. We get some of those homework as well later on. Therefore, how do I do that with the Mohr circle? With the equation is simple. You just put that in your calculator. Is that correct or not? You just come with a number. How do we do it with circle? Same thing as we did it for the Mohr circle. What rotation do I have? From x and y, I have to go negative 40. There I have to go negative 80. So all I have to do, get x and y, because this is the representation of x-axis, and I go how many degree? That's it. So that's the answer. So you go to x prime and y prime. But that angle total is 80 degree. So you call this angle phi, and you calculate the angle phi first. The phi become equal to 2 theta, 2 times 40 degree. Is that correct? Minus 2 theta p, because you already calculated 2 theta p. Is that correct? Because this is really, you do not start from a and b. Always everything start from x and y. That's what you were setting it up. Is that correct or not? And therefore, 2 times 40 degree minus 29.6 degrees, so it becomes 50.4 degree. So that angle is now 50.4 degree. The rest is geometry. The rest, everybody can see what's happening. It's really not a big deal there, but you have to do that. There are a few problems coming here. 1 or 2 problems here maybe requires there. We'll see that as we go along. So therefore, I don't need that anymore. In order not to make this simple to see, I need to read the coordinate of that point. Yes or no? The coordinate of that point, if I make this line going to this point, it is O to H. Is that correct or not? OH is sigma x prime. Yes or no? This is x of that point, and that is, this is sigma, and that is tau. Is that correct or not? Yes? But that's sigma x prime, and that is tau x prime, y prime. Yes or no? So how do you calculate sigma x? Sigma x prime become equal to this length OH, which is OC. OC was sigma average. OC was 4.05. Go back again. 4.05 was OC. So in other words, let me put it this way. We need to calculate the length of OH, which is equal to the length of OC plus CH. But that become equal to 4.05, which was sigma average. And for this length, this is R time cosine of, this is R, this is less than R. Is that correct or not? R time cosine of phi. So plus R, which is 9.49 times cosine of 50.4 degree. And together, I believe it becomes, get your calculator, get those numbers, 10 point something. So it becomes 10.1. 10.1 KSI. For sigma y prime is on the other side. It's here. This is the y prime, so I need OK, this length. I need that length. Is that correct or not? However, I use the same process. I start from C. So I go forward, then minus R cosine phi. Everybody see what I'm talking about? Because this is the same phi. Is that correct or not? So you use the same process. So you need OK. That was OH. So this is OK, which you have OC minus CK. So it becomes equal to 4.05 minus 949 times cosine 50.4. Or this time you end up with minus 2 KSI, which is on the negative side, minus 2. Correct? Of course, this is not in the scale. Correct? Mm-hmm. Right. The last question is, so this is what we are doing now. So what we are doing here is this. We are drawing our element like that. Is that correct or not? Sigma x prime is how much? 10.1. Well, sigma x prime was 10.1. 10.1 KSI. This is x prime, this is y prime. Sigma y prime was negative 2 or 2 KSI. Is that correct or not? Now here is this. If you answer me this question, then I know you know your Mohr circle. Notice what happened here. This is the shear stress, yes or no? So let's calculate tau x prime y prime. Tau x prime y prime is equal to how much? Look at this picture. Look at this. This is r and this is r sine. Yes or no? So it is r sine of phi. Correct. R sine of phi. And that is become equal to 7.31. 7.31 KSI. However, this was not my question. That's obvious to you because this is 7.31. This is also 7.31. Yes or no? But this one is positive. This one is? Which one is the real one? That's the magnitude of the tau xy. Remember that. If I want to put it there, is it plus or minus? Can you answer me that question? Anybody who answered me that question, you are already fine. Yes.
So the x prime, that would, on the state of stress, would actually be positive?
Yes, exact. No, I don't know. We'll have to see what happened there. I don't care about positive, negative. Here on the x prime, actually it shows negative. On the y prime, it shows positive. This is negative. That's positive. Yes or no?
Yeah.
Do exactly the same thing. On the x prime, it is negative. Which way should I go? Up or down? Up. Very good. That's it. Everybody see that. On the y prime, it is positive. Which way should I go? That way. Yes or no? Therefore, I should go like that way. So we end up with the original format. Yes or no? You know why? Because once we went in, we changed the sign. When we came back again, we changed the sign. Twice negative, again become positive. Yes or no? We changed the sign twice, so we should get back to the. Now, is it plus or minus? Plus. You see, look at this one standing here. This is x prime, this is y prime. It's going that way. Therefore, it's plus. Is that correct? Because this is the nature. However, if x prime was here, y prime was there, then it would have been negative. Everybody's got because 1 plus 1 by. That's the nature of the Mohr circle. Because the Mohr circle was like that, we opened it up by using 2 theta instead of 1 theta. Everybody understand that? Yes? Correct? But eventually you get the same thing. Understood? Okay, everybody? You're awfully quiet. Yes? Are you okay? More or less. Okay, it better be more than less. Is that correct or not? So, however, that means you have to look at all those problems, start from the beginning as if you have gone, I know that through ME 218, but if you haven't learned it, you need to learn it. Half of discussion in this class is all about what some of the material we talk about it. In a minute, you will see how complex this will come, but it's really not that complex if you understand the basic. Is that correct or not? Now let's go a little bit further. This is all I can tell you. It is there. We are using the same sign convention. Guy, any shear stress going this way, call it positive. If it goes that way, call it negative. Is all I'm saying that. But you see, but the format of that, look, if it goes like that, this one is, which way is going? Negative way. This one is going positive. That's all the way this Mohr circle being constructed. Is that correct or not? Yes, that's the nature, because that's when we plot it, we use the same technique here. Remember, I call this plus and I call this minus. Is that correct or not? So I'm using the same technique to read it back. Is that correct or not? Yes? All right. Now, let's go back further to this idea. Now, everything so far was related to all that line 1, 2, and 3. Line 2, 3, actually, you have to go through the system, find the state of stress yourself, chapter 1 to chapter 6 again, and then plot the Mohr circle for that state of stress, which is a complete problem. Is that correct? So I give more weight to those two problems than the other one, because the other one, the solution is in the solution manual. Everybody understand that? Yes, or a typical drawing circle or using equation. Now, what is important now? To recognize the whole system. Didn't I say this is the state of stress? Yes or no?
Yeah.
Okay, what do we call this state of stress? You have heard me saying in ME 218. It's very important to recognize. There are, first of all, not 2 axes. There are 3 axes, X, Y, and Z. The reason that we did that, if you go back to the page 2 of your handout, the stress was coming from all three directions, yes or no? Sigma x, sigma y, and sigma z, yes or no? And therefore, everything was in a form of cubic. Should be shear stress here, shear stress there, normal stress here, and there were two more here. Everybody understand that? Then we said this, look, this is too complex. We don't want to do our design like that. Then we make an assumption. It's very important. Look at again in chapter 1 in your book. This cubic has been drawn there. In your handout, go to first page of your handout or second page again. Guys, put your handout in front of you. Here it is. Page.
This first handout?
No, it's on page, I'm sorry. It's on page 15. Is it page 15? What page? Oh, no, page 18. The same page 18. No, I didn't show that the entire series. Let's see, where did I show that? Yeah, okay, here. Anyhow, the idea, no, the page 3. Go to bottom of the page 3. That is general state of stress. Everybody see that? Bottom of page 3, yes? The stresses can go in the x direction, y direction, and z direction. We have 3 normal stress and we have 3 shear stresses because tau xy equal to tau yx. Remember all of that in chapter 1 of your ME218, correct? Then suddenly we decided, this is very important, half our lecture related to this discussion, guys. Then we decided not to put anything here. Everybody understand, which I'm putting it in purple. You want to write it down, everybody, without any exception. We assume sigma z to be equal to 0. And also we assume tau xz, which is here, this is tau xz, and equal to tau zx to be equal to 0, and tau yz equal to tau zy equal to 0. Nothing here, I just put it here, but I'm going to erase it. All of these 3 were assumed to be equal to 0. Notice this cubic had 6 unknown, 3 sigma and 3 shear stresses, 3 normal stresses, 3 shear. By doing that, which has a name for it, what's the name of that? Anybody recalls?
Combined loading.
What?
Combined loading.
No, don't make it worse, please. It's called plane stress. These guys, you have probably heard that. Actually, this is why the problem is with the way we teach ME218. Entire ME218 and entire undergraduate design is based on plane stress. In other words, if the airplane is sitting on the ground, you can design it because when you look at the body of the airplane, there is nothing coming from the air side except air pressure, yes or no? However, if this airplane goes to the sky, that's not the case. Everybody knows that. There are going to be forces there. Is that correct? There no longer it is a plane stress scenario. Everybody understand what I'm saying there? Yeah. Yes? Or you put it on the bottom of the ocean, an object, it is designed like a submarine part or pipe. You put it on the option, it is in here, or in the bottom of ocean, there is sigma coming from all different sizes. Is that correct or not? So look what happened here. Because of this being 0, this being 0, and then this and this here, we only left with sigma x, sigma y, and tau. From 3D, we went to 2D. That's why we call it plane stress. So please remember this word. So all your design, basically undergraduate work at this level of the work is plane stress. When you go, some of you will go to graduate school. I noticed one of my students who was grading for me last quarter, ME218. He came to me today with good news. He was accepted for graduate school with some scholarships, so it was all a smile. Next September he's going there. But he was good at everything. Everybody understand that. Some of you probably will get there. Everybody understand that. So when you go there, then you want to go graduate work, of course, all the design will be 3D design. Everybody understand it. It's not that simple. Then you have more stresses, more format. Anyhow, but for time being, we are only using plane stress. Look what happened. Then, because of that, I can show that as a plate. So everybody see what all of this is square. But look, I show sigma x, sigma y, and tau x. That's what you were saying everywhere because we don't care about this step. Nothing happening there. Is that correct or not? But that's in actuality, that's what happened there. Now, let's go a little bit further to see what happened here. Now, let's assume that I give you, I'm going to erase that. Remember, this is something you have to remember because when we go to the strain and the more circular strain. It's all about this. Everybody remember that. That's very important to recall. Now, we're going to this state of stress, which we have sigma x, sigma y, and tau xy. Notice 3 unknowns. So it refers to 3 equations of equilibrium in 2D. So in other words, it's a 3D object, but we design it as a 2D approach to it. Is that correct? Because we look at all the surfaces. Surface of the shaft, surface of the beam, etc., etc. Yes?
How come you don't put the shear arrows on the bottom side of the square as well?
Yeah, that I cannot show it there. There is bottom. It's also, you see, if I show it, see here underneath, I can not show it. So that's what he's saying, correct. So if I have, you see, we had that. Of course, you see, but in this, I have to show it like that. It crowds the system. Yes or no? In 3D, that's what you see. But actuality is like that. You are right. So this is what we are showing. Sigma x, sigma y, and all the taus. Correct. Everybody see what I'm talking about. This is the 3D approach to that one. All right. Is that understood? Now, what we did here through this entire system is this guy. We started with an x and y. Then we went to a transformation to get to what? To get to the principal stresses. Yes or no? Okay. Now let's do the same thing here. Let's say that we do this, and this ends up like that. So if I change that, there we went clockwise. Sometimes you have to go clockwise. Sometimes you have to go counterclockwise. Let's say this is not the same problem. This is similar, the same. But let's say that we end up like that for principal stress. So this is our principal stress. Yes or no? Correct? This, which axis is this? This is principal 1. Yes? This one is principal 2. Yes or no? We did it here earlier. I erased it. We went from x and y. We went to a and b. The picture was in the bottom of the page 18. Is that correct or not? Yes? Mm-hmm. So therefore, we end up with like that. In this transformation, we have gone counterclockwise. What happened to this axis? Z-axis there. Notice I said from now on, for this discussion today, you have to recall, there is not 2 axes. There is x, y, and z. We rotate this. How did we rotate? I show it one more time to understand what I'm saying. It's very important to recognize that. Is this a stress there? Yes? I went this way to get rid of shear stress. Yes or no? This is now principal stress. This is principal 1. This is principal 2. Obviously, this is principal 3, but it is 0. Yes or no? Correct? But what rotation is this? When I want to go from this system to that system to that system, what I'm rotating now? Look at rotation about the? Very good. So what I want you to write is this. You draw. Forget about that. That's for reference. So you draw this. So, okay, you come up with a circle, any circle. Is that correct or not? When you end up with that circle similar to that or similar to that, but will you do this rotation one more time? When you want to get rid of that shear, you go to the right, to the left, or sorry, clockwise or counterclockwise to get rid of the shear to come to the principal stresses. Yes? So sometimes they call it principal 1, principal 2, and principal 3, which is the Z as well, or A, B, C. You see 2 pictures, 2 handouts that I gave you. One book use A, B, C. I rather use A, B, C rather than P1, P2, and P3. Those are principal axes or principal direction. Is that correct or not? Yes? Mm-hmm. Correct? Now, all this is rotation about. So you do the same thing as we were doing before. So if I started with X and Y, which is here, X and Y end up to A and B. So this rotation, right, the rotation about Z-axis. Yes or no? Correct? Okay. Therefore, this tau, this was tau max. Yes or no? Yes? Tau max, which is equal to R, magnitude R, we are calling it in plane shear stress. Why in plane? The reason is like that. There is a, look at, if I'm showing this rather than square, I'm showing it like in the plane of x, y as we were doing it. Look where this is rotating. Look at this. Yes, this rotation is about the z-axis, which is that circle. Yes or no? These are all the stresses possible through this rotation. Yes or no? But isn't that two more axes that I can rotate this object about the, can I rotate this about the y-axis? You see, when you are rotating about the z-axis, you are changing this constantly. Is that correct or not? Yes? If you rotate this about the y-axis, then you have to take y and z and rotate it about the x-axis. Or if you go like this, then what rotation is that one? That is rotation about the x-axis. So every time you do that, notice what happened here. Again, the key. As soon as I am here, I go a little bit this way and a little bit that way, the shear reappear. Yes or no? Yeah. Therefore, every time I do that, that's why I'm going from here, I go to that point or that point, suddenly I see this much shear. Is that correct or not? Only at A and B, I don't see any shear. Is that correct or not? So that circle represents all the rotations, 360 degree going this way around the z-axis. Is there another circle between y and x, or y and z? Yes or no? Which one is that one? Is that A and B? Look at it. Is associated, let's call it, we went from x, y to x prime and y prime. If I rotate it other way around, so I get this is A, B, x prime, y prime. Yes or no? This is the z or c. Is that correct or not? If I draw this circle, what circle is that? That's rotation about the other axis. Yes? Yeah. Didn't get it? Look, you have this system and you are going this way, yes? All the time. You draw that circle, correct? Now, take the same element with the same stress, assume x is constant, rotate it this way, yes or no? So when you rotate it that way, you are rotating about the x-axis. So you should get another circle, yes or no? But this one, x is out of this picture, yes? So here, look. Here, this circle, it is actually nice to see this way. This is x, all the x prime, y prime, yes or no? All this circle are x prime and y prime. This, look, which one is out? Z is out. Is that correct? Or, by the way, where is Z? Let's put the Z. I'm sorry, I have to say that. This is A, this is B. Where is Z? Z equal to how much? Stress at Z direction is equal to, let's write that sigma in the Z direction was equal to 0. Yes or no? So where is that point? That is it. That I forgot to mention that. So there are the three axes there. X prime associated, x and x prime. This is x and x prime. This is y and y prime. This is z and z prime. Now, if I take this circle, this was between x and y. This circle is between y and z, so rotation is about the x-axis. And this circle is between x and z, so rotation is about the y-axis. So the stresses can happen on all of that. Yes or no? Correct? So therefore, from now on, look, I put here absolute maximum shear. Which one of these three circles now has the maximum shear? X and Z. How much is that? Tau max, write it down. This was in plane shear. The tau max here, actually for this problem that you saw here, tau max is equal to 1/2 of sigma A. Yes or no? Yes? Which is much larger than this one. Correct?
Now this is only a larger circle when the
Yes, there are different options. Yeah, just okay. If that's what happened, this is the scenario. Is that correct or not? Not for this one. You see what he's looking? He's ahead of me and ahead of us a little bit. He looks at this one. This is x and y. Yes or no? Where is z? Z is here. So the other two circles are inside, so it doesn't have effect. I didn't tell you that trick now, but I'm going to reveal that. Just give me 1 second. So what happened here is this, guys. So this is what's going to happen. If your circle, original circle, is here, yes or no? Original server usually is x and y, yes or no? So these are all the rotation about the z-axis. The one that is out is the z-axis. Z-axis, you said 0. Is that correct? For plane stress, it's 0. Yes? Therefore, if I want to have the rotation here and there, I have to draw 2 more circles. Yes or no? That's one thing. The second thing is, where are these shear? I'm talking about rotating this and that one, but where is this shear, that one here? This is here. This shear, this is tau. Let's write it one more time. Tau max here equal to R. This is in plane shear. Can you tell me where is this compared to that one? Now, this is what perhaps I was keep pushing here, but I don't know how much. Is this principal? Yes or no? Is this shear? This angle is how much? 90 degrees here. On the XY axis should be 45, correct. So if this is the plane of principal stress, where do you think the plane of the shear is going to be? 45 degrees to that, yes or no? Where is that falls? Look. Is that 45 degrees to, see, this is the plane of principal stress. Put your hand here, everybody. Put there in that diagonal. Go 45 degrees. Where you end up? You end up in that diagonal. Is that correct or not? That if this number, for example, is what we got there, R equal to in plane was, how much was it? In plane is 949. That 949 is in this direction. Everybody understand that? That's how you plot it. I erase everything. Everybody understand? One is 45 degrees to the other one. Yes or no? Yeah. Correct? So that's it. However, where are the other one is very interesting. I want you to know that. You see, I just show it here. You understand now what I said here. This is original state of stress. Yes or no? You train it around this way or the other way to get to the principal stresses. If I go this way, this is rotation about the z-axis. This is 45 degrees. The shear is here. Everybody understands. However, I can do this. Where is this shear? This is the shear about the rotation about the y-axis. And the other one that goes perhaps from, there is one more there. One more there, rotation about this axis. Everybody understands. So we have 3 of them. We don't have one. Like, because you have a knife here, something you want to cut it, you can cut it like that. Yes, or you can cut it like this. You see that there is 2 different planes. And that's exactly what these 3 circles are. This is rotation about the z-axis. So it's 45 degrees to that. However, if I use the other circle, look at what happened there. The other circle, if I use this circle, which is this one, which is between y and z, that's the rotation about the x. Actually, the shear goes like that, from here to there. Everybody understand what I'm saying? One more time, I'm showing it here. This is rotation about the z. This is rotation about the y-axis, and so far. Everybody see that? So you can, but we don't care about the plane of that much as we do care about the magnitude of that. So all you have to do is this, the following. Draw the original circle, yes or no? When the original circle falls into the place, you don't have to do anything. You get sigma average and you calculate A and B, yes or no? Then you look at this one, sigma z is equal to 0. Is that correct or not? Immediately you draw. If this is the case, that's what he was saying. If this is the case, I'm going to explain it one more time. It's very simple. So what I did not reveal to you is that when we go to the pressure vessels next week, pressure vessels are like that. There are tension going here, tension going like that, so you get this scenario. So this scenario is not yet happened in all your homework. This is something I didn't tell you guys. I knew that, but I never tell you because I didn't want to rebuild the case. This is sigma A is positive, sigma B is positive, therefore both having the same sign. The other 2 circles, you always do that. You draw the original circle in black as you see it in your handout. You draw the other 2 circles in between these 3 points. That's all you have to do, right? And tau max here is, in this case, is not. This is in plane. Absolute tau max, this is absolute. All of them together. Actually equal to 1/2 of what? 1/2 of, this is 0 and this is sigma A, correct? The radius of this larger circle. What's what's the radius of that larger circle? 1/2 of sigma A. So please write it down. In general, this is the equation, guys. Tau max always equal to 1/2 of, I'm going to do an example, equal to sigma max minus sigma minimum. This is always the case. This case, sigma max among all three axes. This is x-axis. Look, x, y, z become A, B, C. Everybody understand that. So you get three principal stresses. One of them is 0, yes or no? The other one at some number, I don't care. In this case, this is tension, so this is tension, this happened like that. So this becomes the case. So as a matter of fact, it become equal to tau max, become equal to 1/2 of sigma A minus 0. So that's what I said, become equal to 1/2 of sigma A. Is that correct or not? But this, which plane is this now? See, these were all the x and y, yes or no? This one was x and z, that's right. And this one was y and z. So if I'm using this circle, so this tau max is in yz plane. So that's what the final decision. Now, actually, it's much simpler than that, guy. So I tell you, that's what you were referring to. All you have to do is the following. Please write the rule down. Write the rule down. Actually, it is much, much simpler when you do this homework. And if I had time, I would do an example, but rest down and I do the example next time. Write down in your note. If sigma A and sigma B, the two original principal stresses, have the same sign, these are the scenario. I just did that for you. This is the original circle. What's the same sign? This is positive, this is positive, the same sign, means both being tension, yes or no, correct? Right, sigma A and sigma, you say sigma A ends up to be 20 KSI and sigma B ends up to be 8 KSI. Both are positive. Therefore, your three circles become like that. Is that correct or not? Yes? However, another alternative would be that both become compression, because you may put compression, but they have the same sign still, yes or no? Therefore, where is the other two circles? This is 1. This is 2, the other one is 0. Is that correct? Because sigma z is 0. That's what we are talking about, plane stress, correct? Yes? So therefore, that goes there. And the other one goes, still that's it. In this case, always tau max, which is out of plane. Out of plane. Now again, one more time, I'll show you what is the plane and out of plane. Now you understand, appreciate that. In plane, because we show that as a square, not as cubic. That is square remain in this plane. Everybody understand that. Original circle, you were doing this, yes? Now you are doing this and that as well. Is that correct or not? So that's why this one is called out of plane. This one is called, the original one is called in plane, because you are not moving it, that is your element from out of plane. Therefore, in that case, this is applied. Where was I was showing here. That's right. In this case, when I was writing it somewhere, I forgot. Oh, there. So when is this scenario and that scenario, that become equal to 1/2 of sigma max minus sigma minimum equal to 1/2 of sigma A. But assuming this is A, this is B, this is C, this is A, this is B, this is C. Is that correct or not? However, as he was noticing in there, sometimes sigma A and sigma B are having different signs. So that's the second option. So write it down. This is on certain problem, option 1. This is option 2. If sigma A and sigma B, as you did it in all your previous, have opposite sign, opposite sign, then this is going to happen. One is going to be one side, the other one going to be other side. Yes, one in tension, one is compression. Where is sigma z or sigma c? Where is sigma z? At the middle, somewhere in between. So the other two circles are inside, the smaller. Is that correct or not? So if the other two is smaller, therefore, that issue never arises, yes or no, correct? So that is what you had for the shaft, for the beam. This I didn't reveal to you. In never, when you design the beam and the shaft, go back, check all your homework, except the one that they given it at this form. All the one you including 1 and 2 there. Everybody, when you're designing the shaft and the beam, always one principal stress become positive, one principal stress become. You never saw this before until today. Why you are seeing it today? Because next week I'm going to talk about pressure vessels. In pressure vessels, that's why we left that one out. I don't know, some of you may have covered pressure vessels. Have you, any of you have covered pressure vessel in ME 218? Because it was supposed to be 218, we run out of time, so we always leave it for that. Because quite frankly, if you don't, that's why I changed my syllabus too. I don't know whether you noticed. I was supposed to talk about this in week 7 or week 6, but I thought if I want to talk about the pressure vessels really for you to understand it, I better bring this a little bit forward, hoping that you all understand what I talk about it. Is that correct or not? So therefore, because really it's procedural, everybody see that, it's very simple. All you have to do, draw your original circle and then draw the other 2 circles according to X sigma z. Is that correct or not? So by doing that, you can find one of the radius of the larger, still the radius of the larger circle is your maximum, absolute maximum shear. But it could be in plane, it could be out, it could be this way or it could be this way. Everybody understand what I'm saying? And those pictures all being in color showed in your handout. I hope that some of you printed in color. It shows, look at it, handout, the second handout, the first page and second page of the handout. They show all 3 directions. We really don't care about direction. If still you don't get the direction, okay, I don't care, but you need to find a magnitude of this shift and to know what the in plane and out of plane are. Is that correct or not? So the idea, one more time, repeating, all you have to do, draw the original circle. It just happened to be category 1 or category 2. That's as simple as that. Is that correct or not? However, what I'm going to do next time, which I did it for other class, I'm going to put the object under the water. Then what's going to happen?
There's pressure on all sides.
There is a sigma coming from z direction. So we can do certain problem that we couldn't do before with this. Then I have to bring sigma z not equal to 0. Sigma z equal to the height of water. Everybody, well, I'm going to do that. Don't worry. But don't lose track of that. In order to understand again what I'm talking next time, you are supposed to do all this homework this weekend. Please start doing it. That's all I'm saying. That. Yes. Don't like the other guys say, today is not my day. I don't want that. I want your day every day. Is that correct or not? Yes. But you have to come and ask questions. You have to do your homework properly. Yes.
I was just going to ask, so it's probably getting ahead, but do the 3 axes always have to be on the same line?
Yes, because they're all sigma. Yes.
So they all
Yes.
are on the same line always?
Yes, because it's pure sigma. Yeah, right. Because they are pure stress, no shear. You are talking about the axis here. You are talking about principal axis. Yes. ABC. Yes. ABC doesn't have a shear. Remember that? Yes or no? Okay.